we're sort of sad to see him now build us coming from Columbia. He still has a Stony Brook connection, though, and we still think of him as part of the family.
I'll be back next year.
Good. And he'll be talking about developments in four-manifold topology arising from a theorem of Donaldson.
Thanks a lot, Claude. Well, it's a great pleasure to be back. I haven't been gone that long, but it is a pleasure to be back. And it's certainly a great pleasure and honor to be here and talk at this conference. To me, it's an honor of Simon. As I was thinking about what I would talk about, I thought, well, this is a conference in honor of Simon. I think the audience is going to be basically from the geometric end rather than the topological end of Simon's purview of mathematics. And as I look around, I see that with very few exceptions, that turns out to be true. So I thought I would talk about some of the more topological aspects of some of Simon's early work. I guess how shall I put this? The rubric for what I'm going to say today, or the message I'm going to try to get across to you, well, there are a couple, but one of them is a maxim that I learned from Bill Browder when I was a young instructor at Princeton, which is there's no substitute for a good idea. So I'm going to talk about a good idea that Simon had when he was a graduate student or shortly thereafter, that's led to an enormous, beautiful tapestry of mathematics over the last 30 years as Simon and others have developed this idea that he had, and it and its progeny now pervade a tremendous amount of topology and geometry. Now, I couldn't in an hour possibly do justice to that tapestry. I'm going to follow one thread in, but you understand that it's one thread in an enormous carpet. And that thread is part of how you use Donaldson invariance to study the topology, the smooth topology of four manifolds. And the other reason, the other message I would like to get across in this talk is, let's see, maybe I can make an analogy. Your cell phone and email and Twitter and so on are very efficient and allow you to communicate very quickly with the world, but I think we're beginning to see that in that efficiency something is lost. A depth of interaction, a depth of thought, a depth of conversation about whatever the subject is. Well, I see an analogy, hopefully I see an analogy in the area of mathematics that I'm going to talk about. These Donaldson invariants that I've already referred to turn out to be incredibly powerful. They come from beautiful geometric and topological objects, but they're often hard to apply. You have to do a lot of hard work to use them. And there have been more efficient versions of these invariants that have come along since, the Seiberg-Witten invariants, even some purely topological combinatorial versions of these invariants, which are easier to use. But those moduli spaces don't have nearly the beautiful structure of the anti-self-dual moduli spaces, and I think something has been lost or forgotten, and I would like to make a pitch for these anti-self-dual moduli spaces. I hope in this talk I convince you that there is a lot of interesting geometry and topology by showing you one very low-dimensional and simple case. And I am hopeful that, in fact, these moduli spaces won't totally be forgotten and that they do have more to teach us, more than Seiberg-Witten invariants or the various Heegard-Floer homology invariants, which are beautiful and powerful. I have nothing against them, but let's not forget the anti-self-dual equations. All right. So let me just start very generally with the background of the smooth topology of four manifolds, and I'm focusing on the question of classification. Can you classify them? What do they all look like? Well, let's start negatively. It's not possible to classify smooth four manifolds in some very technical, logical sense. You make a list recursively, exactly one manifold, four manifold out of each diffeomorphism class, and then given in some recursive way a four manifold, figure out where it is in the list. Of course, the paradigm for this is surfaces, where we list the surfaces, say the closed-oriented ones, by genus, and if you're presented a surface, say, as a triangulation, you calculate its Euler characteristics so you know where it fits. So let's do that for four manifolds. Can't do it. Can't do it for manifolds of any dimension greater than or equal to 4, because in fact there's an algorithm to start with any finitely presented group and construct a manifold with that as fundamental group, and you can't classify, in this sense, finitely presented groups. So when presented with this obstacle, what do? Well, one thing we can do is back off and try a smaller question, simply connected four manifolds where this objection doesn't apply. So that's what we're going to talk about today, simply connected four manifolds. So let's just start with the simplest invariance, the homology. So the only non-trivial, the only interesting homology group is the second homology or second cohomology. The first and third are trivial. The zeroth and fourth will be Z because it's a connected manifold. And the second homology has an interesting algebraic structure. It's intersection pairing, which is a cup product from H2 to H4, and then evaluation on the fundamental cycle. You get a symmetric unimodular pairing on a free abelian group of finite rank. So if you choose a basis for this free abelian group, this pairing is represented by a symmetric matrix. Unimodularity means the matrix is invertible over the integers. Its determinants plus or minus 1. You change a basis, you change the quadratic form in the usual way. And this is the only homological invariant of a simply connected four manifold, and it turns out that it's also the only homotopy invariant of a simply connected four manifold. So an old theorem going back to Whitehead says that two of these manifolds, closed simply connected four manifolds, are homotopy equivalent if and only if these homological pairings are isomorphic up to a sign, because I can reverse the orientation of the manifold. And a much more recent theorem, dating from the same time that Simon was doing the work that I'm going to be talking about, Mike Friedman, is that in fact this is the homeomorphism classification of smooth, simply connected four manifolds. The two of them are homeomorphic if and only if they're homotopy equivalent. Okay. There's one other result that dates from prehistory, the 1960s, due to Terry Wall. If you have homotopy equivalent smooth four manifolds, then they're H-cobordant, meaning that there's a smooth five-dimensional manifold with the two ends, these given four manifolds, so that the inclusion of each end in looks in homotopy theory like the inclusion of M cross 0 or M cross 1 into M cross I. But the statement is only homotopy theoretic. These are nice smooth manifolds, but the inclusions are only homotopy equivalences, not inclusions into a product. Okay. So if you have two homotopy equivalent four manifolds, they are connected by something that looks homotopically like one of them cross I. And it's a nice argument using a little Morse theory from that to show that, I'm missing a prime here on one of those, that the two manifolds become the same after you take connected sum with enough S2 cross S2s. So, it's beginning to look like they're not so far apart, even smoothly. So this, of course, is it's a diffeomorphic. That's a smooth statement. All right. Well, this is a question of uniqueness, or how do we tell manifolds apart? How do we construct them? Where do they come from? Well, the obvious source is algebraic surfaces. And a lot is known about algebraic surfaces. In some sense, they've been classified, or a partial classification at least, and a lot of topological information is known about various algebraic surfaces. So that's a starting point. There are some topological operations you can do. Some are inspired by things in algebraic geometry, others are not. So they're connected some. If you have two manifolds, you can connect them together. There's sort of by mimicking algebraic geometry, if you have two smooth surfaces that meet each other in a curve, and the normal bundles in the two manifolds are inverses, you can smooth that like you smooth an ordinary double point, make a new surface. Turns out if you have a two-sphere embedded in the four manifold with a trivial normal bundle, there's a nice transformation called Gluck surgery or Gluck transform that produces a new four manifold. We have no idea if it's different or not, but it isn't obviously the same. That's not something that comes from algebraic geometry. And then there are versions of log transforms, which I'm going to talk about a little bit, that you can do on two tori with trivial normal bundles. And there are other similar sorts of topological constructions. The trouble is we don't have a whole lot of invariance to decide whether or not, if we do one of these constructions, we produce something new and different or not. Now, one thing I have to tell you about algebraic surfaces, if you don't already know it, is that surfaces come with moduli, continuous or smooth moduli. They come in families. So we're going to say that two surfaces are strictly deformation equivalent if there's a threefold that with a smooth proper map, well, I think I mixed up. A smooth proper map, sorry, I confused two things. This should be an n-fold, smooth proper map to a connected smooth variety with one fiber isomorphic to S and the other isomorphic to S prime. So if you can put S and S prime in a smooth family over a smooth base, then S and S prime are strictly deformation equivalent. This generates an equivalence relation which is called deformation equivalence. So if you have a sequence of surfaces, each one strictly deformation equivalent to the next, then the two ends are deformation equivalent. And it follows immediately from this and the local trivialization of these families that algebraic surfaces that are deformation equivalent are automatically diffeomorphic. Okay. And for the rest of this talk, I'm going to consider the diffeomorphism classification of simply connected algebraic surfaces. Okay. So let's talk a little bit about algebraic surfaces qua algebraic surfaces before we get into the topology of them. So the first invariant of an algebraic surface is called its Kadira dimension. And this is the dimension of the image of the surface under the map to projector space given by the sections of the canonical bundle. So this map's only going to be birational in general. Sorry? Sorry. You're right. Powers of the canonical bundle. So, in fact, there are examples where there are no sections at all. That's Kadira dimension minus infinity. You have no map. And then otherwise, you actually get a map and you look at its dimension of the image. So, those of Kadira dimension minus infinity are either rational surfaces or ruled surfaces. Those of Kadira dimension 0, these are the Calabi-Yau surfaces. Well, there's the K3 surface. There's something called the Enriquez surface, which has a Z2 cover, smooth. It's got fundamental group Z2, and its universal cover is a K3. There are, of course, the abelian varieties. And then there's some hyperelliptic surfaces, which are finitely covered by products of elliptic curves. So these surfaces are fairly easily classified, topologically at least, and some people would argue with this, but they're rather uninteresting.
Yeah, I think you have to delete that.
I knew Bob was going to object to that. Among these simply connected ones, the simply connected ones are rather uninteresting and easily classified. These are topological statements, not algebro-geometric statements. Okay. Surfaces of Kadira dimension 1 are elliptic surfaces. So they admit a map to a curve so that the generic fiber is an elliptic curve, a curve of genus 1, smooth curve of genus 1. Surfaces of Cadaver dimension 2 are said to be of general type. In fact, in some sense, we don't know a whole lot about these because there are a lot of them, but in another sense, we have strong finiteness results. So if you fix the total rank of the homology, then there are only finitely many deformation classes of surfaces of general type with that much homology. And that will come up later. But in no, correct me if I'm wrong, Bob, in no sense do we have any kind of classification of surfaces of general type. Bob agrees with that. Okay. So we're going to focus for a while on elliptic surfaces. The 0 and 1 Cadaver dimension minus infinity, 0 being fairly easy to understand. 2 being these general type where we just have finiteness results. So the elliptic surfaces are more complicated or more interesting from this perspective. So if an elliptic surface is a simply connected surface, then its base is automatic. The base of the elliptic fibration is automatically CP1. And if all the fibers are irreducible curves, then a slight deformation of the surface and the projection allows you to arrange that the only singular fibers are fibers with a unique single double point, non-degenerate double point. And the number of these double points is automatically divisible by 12. And when you divide by 12, the answer you get is the geometric genus of the surface plus 1. So the smallest number of double points you can have would be geometric genus 0. That would be 12 double points. Okay. Now, there's an operation, I've referred to it in passing earlier, called log transform that starts with one elliptic surface, does a complex analytic transformation, and produces another one having a multiple fiber. So let's start with an elliptic surface and a smooth fiber. Let's fix a positive integer p and a p torsion point in pic naught, in the line bundles or divisors. Then if you fix a point in the fiber, in this elliptic curve, then there's a unique second point, y, such that the divisor associated to this element tau is in fact linearly equivalent to y minus x. As you move x around, y will move around, so this determines for you a translation of the elliptic curve of order p. If you take this thing and write it as isomorphic to complex C model lattice, then this will actually be a translation in C of order p determined by this element tau in pic naught. Okay? Oops. So now let's take a small disk centered at the point in the base curve. So centered below the image, centered at the point which is the image of f. And then for each z in that disk, let fz be the fiber over z. And this p torsion point at the central fiber, call it f naught, in fact extends uniquely to a holomorphically varying family of p torsion points in these varying elliptic curves. And by this construction I just talked about, we get then a holomorphically varying family of translations of order p of these various elliptic curves. So now I'm going to make, so now take the map of the disk to itself, which is the p-sheeted ramified cover, ramified at the origin, which is the image of our original fiber. Look at the pre-image in the elliptic curve of the disk delta. Pull back by this map, and you get a family u prime over delta prime, which is the pullback of u. Okay, and the p torsion points above delta lift, of course, to p torsion points in the fibers above delta prime. And there's a natural action of the cyclic group of order p on u prime that acts by, that rotates the disk by multiplication by the p, generating pth root of unity, and acts on these fibers by, well, acts on the central fiber by this translation we've been talking about. Okay. So we can form the quotient, that's a free action, we can form the quotient to get a new family over the quotient of this disk mod the ZP action, which is just the original disk. So we have a new family over the disk we started with, but the fiber over the central point is a copy of the original central fiber divided by that action, that cyclic group of order P. All the other fibers are identified with the original fibers over some point in the original disk. So I have two families over this disk. They're clearly not the same family because one is a smooth family across the entire disk. The other has a multiple fiber over the origin. But using the log function, we can glue the new family over the disk to the original elliptic curve with the central fiber removed. That gluing will take place over the punctured disk. And to write down an analytic formula for the gluing, use the logarithm and these translations. I won't write down the formula, but you can look in any of your favorite books to find it. So the new surface has the same base, and away from this multiple fiber is isomorphic to the original surface, but the fiber at this place where we've done the operation is replaced by its quotient by the ZP action. Okay, did I say everything? Right. And the fiber has multiplicity P. One way to think about multiplicity P is if you take the central fiber and look at nearby smooth fibers and allow the smooth fiber to, say, come into the central one along a path, that family of smooth fibers will converge to the P-sheeted cover of the central fiber. So in homology, the central fiber now is 1 over P times the homology class of the generic fiber. And so that's the log transform. You can do this smooth, in the C infinity category using a very similar operation. This is the analytic version. Okay. Now, if you have an elliptic surface, you can do log transforms at any finite collection of smooth fibers. And if you assume the original surface is simply connected and without multiple fibers, and then you do these log transforms, the resulting elliptic surface is determined up to deformation by the Euler characteristic of the surface you started with, its geometric genus, and the multiplicities of the log transforms you do. It's pretty clear up to deformation it doesn't matter where you do the log transforms because you can move the fibers around. Maybe it isn't so obvious that the P torsion point you've chosen doesn't matter, because in fact there are lots of different P torsion points I could use, but the monodromy of the surface when you go around the singular points generates all of SL2, and P torsion points mod SL2 are, well, there's only one mod SL2. Is this true for arbitrary number of fibers, or is it only true for 2? Yeah, okay. All right. So our new surface up to deformation is simply determined by the surface that we started with, maybe a K3, whatever the geometric genus of that surface is, and the multiplicities we put in. That's the only deformation invariant, and therefore the only possible diffeomorphism invariant. Well, that's what I just said. If the original surface is simply connected without multiple fibers, then the fundamental group of the resulting log transform surface is the fundamental group of the base orbifold. So the base started out to be CP2. Now you've done these log transforms. You put orbifold points in the base that record those multiplicities. So you get an orbifold whose topological underlying space is CP1, and you have at each for the image of each multiple fiber, you have a multiplicity. This is a two-dimensional orbifold that has a fundamental group. For example, if you have 3 or more positive multiplicities, that fundamental group, if you have 4 or more multiplicities, that fundamental group is infinite. For 3, you get some beautiful finite groups and lots of infinite groups. For 2 points, you get a cyclic group, which is the GCD, the GCD of the 2 integers you used. All right? And if you have 1, you get something simply connected. All right, so now I want to talk about a particular construction of log, a particular example of log transforms. Can you raise one of the screens and let me draw a picture? So I'm going to start with the rational elliptic surface. So in projective space, in the projective plane, CP2, I take two cubic curves. F naught equals 0 gives me a curve C naught, and F infinity equals 0 gives me a curve C infinity. So these are both, if I choose F naught and F infinity generically, I will get two smooth cubic curves, elliptic curves, curves of genus 1, and they will meet in 9 points. So here they are, 1, 2, 3, 4, 9. Okay. I do this generically, and those crossings will be transverse. So blow up the 9 points. So for each crossing, you blow it up, you get a line, and now the red one comes through one point, and the green one comes through another. So when you blow up these 9 points, the 9 points of intersection, you get, in fact, you get a smooth surface that now has an actual map to the complex line. One of the fibers is F0, the other is F infinity, and the ones in between are called, let's say, Ft, where the equation for Ft is F naught plus T times F infinity. So this defines, sorry, these should be C's. C, C, C. Yeah. This defines Ct. That would be for finite t. T equals, I got it backwards, didn't I? T equals 0 gives me F naught. T equals infinity gives me F infinity. Yeah, so that's right. So this is a family of elliptic curves. And in fact, what is it? It's the family of, it's the pencil of all elliptic curves passing through these 9 points. So you start with a pencil of elliptic curves passing through this 9 points. There's a one-dimensional family of them. You blow up the 9 points, and you get a one-dimensional family of elliptic curves with no intersections, no base points. Nice projection to P1. So this is an elliptic surface. Well, the Euler characteristic of this manifold is H naught is 1, H4 is 1, and H2 is 10. So its Euler characteristic is 12. So it can't be a smooth elliptic fibration. Now it would have Euler characteristic 0. It has to have 12 ordinary double points. Well, it has to have singularities that give Euler characteristic 12. If I do this generically, I'll get 12 ordinary double points. So this is an example of an elliptic surface of geometric genus 0, obviously, 12 ordinary double points in this family. Okay. So that's the rational elliptic surface. Okay, you can bring it back down now. So that's what we just did. We took a generic pair of cubics, we blew up the 9 points, and we got an elliptic surface, the rational elliptic surface. The definition of a Dolgochev surface is to take this rational elliptic surface and do 2 log transforms to it using integers p and q. I don't have to tell you torsion points or which fibers because we're working up to deformation. So we're going to use p and q, 2 positive integers, greater than 1, in fact, and do log transforms on 2 fibers, 2 smooth fibers, using those multiplicities, and I require them to be relatively prime, so we get a Dolgochev surface. So the relatively prime means that the fundamental group is trivial, because I told you the fundamental group was cyclic of order the GCD, greatest common divisor. Right? So these Dolgochev surfaces are simply connected, and in fact, Dolgochev, who constructed them in the 60s, did he? Early 60s, showed, mid to late, showed they were simply connected. It's not hard to see they have the same Euler characteristic, therefore they have the same, well, they have the same intersection form as you started with, a form of type 1, 9. So one positive vector, one-dimensional positive vector, nine-dimensional negative space. In fact, isomorphic to the intersection form you started with. The canonical class changes, though, and it turns out to be a multiple of the generic fiber. That multiple is a rational multiple, and that's because the generic fiber is, in fact, divisible by this number. So there's an indivisible homology class, cohomology class. PQ of it, PQ times it is the generic fiber, and this is the canonical class of the Dolgochev. So this is the divisibility of the canonical divisor in the Dolgochev surface. Okay, so these are non-rational, simply connected elliptic surfaces of geometric genus 1. Okay. Well, the simply connected surface, and I've told you the intersection form, so all the Dolgochev surfaces are homotopy equivalent, indeed homeomorphic, to the rational elliptic surface projective space blown up. It's also true, and I guess Dolgochev proved, if two Dolgochev surfaces are deformation equivalent, then their multiple fibers have the same multiplicity. So the deformation classes of Dolgochev surfaces are the unordered pairs of relatively prime integers bigger than 1. Okay? Now we leave algebraic geometry and go to topology and to Simon. So I think of this as Simon's second theorem using work from Simon's zeroth theorem. His zeroth theorem being his thesis, right? That's the prenatal output. And then his first theorem was about positive or negative definite manifolds. And this is about the next one up, a form with one eigenvalue of one sign and all the others of the other sign. So I think of it as a second theorem. Simon proved the first Dolgochev surface you could write down in terms of the integers, D23, is not diffeomorphic to a rational elliptic surface, so it's not rational. Okay. This was the first known example of homotopy equivalent, non-diffeomorphic, simply connected four manifolds. It was the first counterexample to a statement, the H-cobordism statement in dimension 4. That's a statement that's true in all higher dimensions and is a basis for a classification of higher dimensional simply connected manifolds. It also was proved by Mike Friedman in the topological category in dimension 4. So this was in and of itself a major advance in our understanding, or maybe our non-understanding, of four-dimensional manifolds, and a complete shock in comparison to what Friedman was proving at almost exactly the same time. This discrepancy between the two topological and smooth topology classifications in dimension 4. This was a revolution. So, just a personal, I take myself back to those times. When I saw Simon's first theorem, I thought, well, that's a beautiful theorem. I really like that. And I sort of listened to talks about it. But I didn't immediately want to jump in and start proving theorems. It just, that's nice. That was great. You know, not a bad start for a career, let me tell you. But when I heard the second theorem, I thought, oh, well, he's really onto something. I mean, this is going to go somewhere. And, of course, it's gone hugely into topology. There was, in fact, I don't know if it was in their book or if this is just something Karen said, but I think it was something she said in a lecture. Uhlenbeck was sort of musing on this relationship between geometry, the anti-self-dual connections, and topology And there was this one point where they collided, Simon's first theorem. Maybe that was going to be it. She wasn't sure. After this, there was no doubt this was the wave of the future. So I began thinking about these things at that point. Okay, so how did Simon do this? Well, let's back up a minute from the Dolgochevs and just think about a general, simply connected, smooth, of course, form manifold of this type, the intersection form. So homotopy equivalent to CP2 blown up at 9 points. So what Simon did was the following. He said, look at the space of irreducible connections up to bundle automorphism, the gauge equivalence classes. And we're going to work with a bundle over the form manifold, an SU2 bundle, and the simplest one, charge 1, the Chern class 1. If you fix a generic metric, well, associated to that metric, there's self-dual 2 forms. There's a line of them, so pick a non-zero self-dual 2 form. Call it omega, and let z omega be the zeros of the 2 form in the form manifold, so it'll be a collection of circles if you've done this generically. Okay, so that's a little bit of the topology. Now, over the space of connections, B, cross the manifold is a natural U2 bundle, P. And if you restrict it to any point in the connection space, cross the manifold, you just get something that's identified with the original bundle, except it's U2 instead of SU2. And if you look at the equation that a connection on this bundle be anti-self-dual with respect to the metric you have, this defines a 2-dimensional smooth submanifold inside the space of connections, script M, calligraphic M. It's called the moduli space of anti-self-dual connections. So it's a nice smooth 2-manifold, and it's oriented by using the self-dual 2 form. In fact, well, I'll say this and then I'll do a picture. If this manifold may not be compact, memory plays tricks on you. When I was preparing this talk, I was thinking, oh, these moduli spaces are compact because I was thinking I was going to apply them in the algebraic world, and in the algebraic world for Kähler metrics, they always are compact, but in general they're not compact. It was a beautiful twist in the argument Simon must have discovered, must have done, I'd completely forgotten about. But anyway, it was there in our paper, and I'm sure it must have been in Simon's too. So this moduli space is in general not compact. Well, it's not compact, and its end is diffeomorphic to the zeros of this self-dual harmonic form cross a half-open interval. And the connections out near the end are highly concentrated connections. So they're flat over most of the manifold, and they have a single bubble that carries the entire charge, and that bubble has to be concentrated, centered near a point of the zeros of the harmonic form. Okay, so you can't use this moduli space as a cycle because it's not compact. It's got an end. But there's a natural way to fill it in. If you look inside the self-dual 2 forms, at the perpendicular to this line that we have, generated by omega, and you take a generic section of that, you'll get a 2-dimensional chain in the manifold whose boundary has to do with the Euler characteristic of the 2-sphere, is twice the zeros, twice these circles. Okay? So then we can form a cycle in the space of connections by joining 2 copies of the moduli space to this cycle. We have to take 2 copies of the moduli space because the boundary of the moduli space is a single copy of these circles, whereas what we get by the Euler characteristic, this chain has boundary 2 copies of the cycle. So we glue these 2 together and we get a nice 2-dimensional cycle in the space of gauge equivalence classes of connections. Well, we have to make all sorts of choices. Where do we truncate? What perturbations to use to glue these things together? But we're talking about homology here, so none of that matters. So would you raise the screen? Let me draw a picture. Thanks. So we have this infinite dimensional space. We have this infinite dimensional space B of connections mod gauge. There is a region in this space of highly concentrated connections. I mean, it's not an open subset. It's finite dimensional. And this is an infinite dimensional space. Think of it as the Taubes map from the manifold across the amount of concentration in infinity. So these are going to be things. This is the amount of concentration. This is the center of concentration. This actually embeds in here. So these are connections that on the manifold are flat, trivial out here, and then have a bubble, and you've picked some parameters of the scale parameters given here. How you actually glue in, well, you have to make some choice, but you do it smoothly over the manifold. You get an embedding of the manifold across this interval into the space of connections. And what happens with your moduli space is it's not actually in here because none of these are going to be anti-self-dual, but it's very close. It gets closer and closer into this Taubes highly concentrated connections. So these are anti-self-dual. These are not, because they're flat here and they're not flat everywhere, so they can't be anti-self-dual. They're not analytic. Nevertheless, you have here this two-chain that I talked about, and then you make a little perturbation and join them here, and you get a nice cycle. Okay. All right. You can pull the screen back down. So as I say, the resulting cycle you get here depends only on the metric and the self-dual 2 form. And on the self-dual 2 form, it only the sign changes. So the self-dual 2 form sits in a line. It's a non-zero form, so there's two components. And all forms in one component give the same cycle up to homology. If you flip components, what happens is you flip the orientation of the moduli space, so you change the sign of the cycle. Yeah, you can go ahead and pull it down. Thanks. All right. So now, using this, you can define an invariant, homological invariant. You simply cap with the second Chern class of the universal bundle. This gives you a map from the second homology of the manifold to the second cohomology of B. You then integrate the image over the fundamental cycle of this enhanced moduli space. You get a function from the second homology to Z, or equivalently, you get a two-dimensional cohomology class in the original manifold. It depends on, it depends on, well, the original manifold, the generic metric, and the choice of self-dual form. But as I said, the only effect of the form might be to change the sign. Choosing a different form would change the sign. Okay, I guess I said all of that. Yeah. Okay. So what we've just constructed is a two-dimensional cohomology class that depends on the metric, the self-dual 2 form. But since we're in the context B2 plus equals 1, we know by general arguments that there will be a dependence on the metric, or there can well be a dependence on the metric. And the point is that in a generic one-parameter family of metrics, GT, there'll be a discrete set of values at which there are reducible connections. We've been avoiding the reducible so far. These values occur exactly when there's an integral class, AI, of square minus 1, orthogonal to the self-dual 2 form for this metric. In this case, the three-dimensional parameterized moduli space has a singularity whose link is the 2-sphere. You might look at that and say, what kind of singularity is that? It's the 2-sphere, you're coning it off. Doesn't look like a singularity, but the point is that this two-dimensional cohomology class does not extend. So it's a singularity of the space in the cohomology class. And in fact, let's just look a little more at this point Ti. So this path of forms crosses this wall where AI is 0, let's say it goes from the positive region to the negative region, then you can calculate fairly easily the difference in this Donaldson invariant on the two sides of the wall, and here's the formula. The value right before you get to the wall minus the value right after you get to the wall is minus 2 times this class. So there's a wall crossing formula as you cross these walls. Okay. Well, I guess I didn't quite finish the argument. Simon then used that. He was able to compute using his 0th result, his thesis, which tells you that for an algebraic surface, you can compute the moduli space of anti-self-dual connections for a Kähler metric using algebraic geometry. He was able to compute the moduli space for the Dolgochev 2-3, and he got an answer which was inconsistent with the rational surface, and therefore these two manifolds were not diffeomorphic. Okay. Well, to go further with this, you need to understand a little more of this chamber structure that I've started alluding to. So we have a quadratic form on this second cohomology, real cohomology now, defined by the square of these vectors. Let's look at the hyperboloid h of m, which is just where the quadratic form takes value 1. That's a hyperboloid of 2 sheets because the type of the form is 1, 9. And for each integer vector, integer cohomology class of square minus 1, there's a codimension 1 wall. I've called it W hat A. Inside the two-dimensional cohomology, this is a affine subspace of elements, well, the linear subspace of elements orthogonal to A. So these exist in the cohomology, and they cut the hyperboloid transversely and give codimension 1 walls, which I've called WA, inside this 2-sheeted hyperboloid. And this set of walls is locally finite and divides this hyperboloid, or each sheet of it, into chambers. And our previous discussion, what it really shows is that for each chamber that has a metric, or has the self-dual 2 form of a metric, there's an invariant, the Donaldson invariant of that chamber, which is a two-dimensional cohomology class. And if two chambers meet along a wall, then there's this transformation formula for how the invariant changes as you cross that wall. In fact, this formula allows us to extend this function from the chambers that contain a metric, contain the self-dual 2 form of a metric, to all the chambers. You just start in a chamber that has a metric, do this transformation law, and it's an elementary fact about reflection groups that you don't get a contradiction if you start somewhere else or go 2 ways from this given chamber out to any other. So this formula allows you to extend this to a function on all the chambers. So this wall crossing halls. And then, okay, so Simon showed that the maps on chambers were different for the Dolgochev and the rational elliptic. And so he had to compute the moduli space, and he did it with a Kähler metric weighted toward the fiber, at least a little bit. And then you can compute the moduli space of anti-self-dual connections, get this result. Okay. But let's go on. It's trying to understand this chamber structure. So suppose you have a point, so this is a 9-dimensional hyperboloid. Suppose you have a point where well, first of all, if 2 walls meet, they meet orthogonally, because, well, they just do. So let's look at a point where the maximal number of walls meet. That would be 9. So let's look at a point where 9 walls meet. We'll call that point a corner of any chamber that it lies in. It lies in 2 to the 9th chambers. Well, if X is a corner, it's automatically an integral cohomology class of square 1. And we define the canonical class of the chamber and its corner to be a formula that, for those of you who know a little bit about algebraic geometry, will look familiar. So 3 times the +1 vector minus the sum of the -1 vectors. Actually, the canonical class in algebraic geometry is the negative of that. But anyway, that'll be the canonical class of the chamber and the corner. Okay. So what Bob and I showed was that every chamber has a corner. It's pretty obvious. But more interestingly, if X is a corner of a chamber, then this canonical class doesn't depend on the corner. It only depends on the chamber. Okay. This is very special to the arithmetic of forms of type 1-9. There is an analogous but much more complicated structure when you replace 9 by a larger integer. Just quite beautiful, but when we had to study blow-ups of Dolgochevs, but I won't really talk about that much. Okay. So we've discussed the Donaldson invariant, one of these manifolds, as a function from the chambers to the second cohomology with a given wall-crossing transformation. Let's define the refined Donaldson invariant by adding in the canonical class of the chamber. So take the geometric invariant as defined by Donaldson and add the canonical class of the chamber. You get a new invariant, depends on the chamber, but in fact, these functions have the opposite transformation law under wall crossing. So this is an invariant, doesn't depend on the chamber. So now you have an invariant, you don't have to worry about chambers, and you might have a diffeomorphism, you don't know how it's going to line up your chambers, so if you're trying to compare two things. But now we have an invariant independent of the chambers, and now let's go back to the Dolgochevs and compute it, or try to compute it. So again, using the same result that Simon did in his case, go back to his thesis, and instead of computing the anti-self-dual equation, let's compute the stability, find all the stable bundles. And that gives us a moduli space, which is related to the Kähler class. And for Dolgochevs, it's in fact copies of the exceptional fibers with multiplicities. And from this, you see that the invariant is a multiple of this indivisible class that underlies the fiber, and the multiple is at least this much, plus possibly more, depending on how many components of various fibers you have. But anyway, you immediately see that the map from deformation classes of Dolgochev surfaces to diffeomorphism types of four manifolds is finite to 1. And also you can get from this that, well, no Dolgochev surface is rational. We were able to explicitly compute in the case of 2Q and see that, in fact, it's 1-to-1 deformation to diffeomorphism for 2Q. And if we knew more about these multiplicities, maybe we could get a better result. But at least this gave us finite to 1. We were also able to do this for blow-ups of Dolgochev surfaces using this arithmetic and chamber structure for n greater than 9. But as I said before, it's intricate and rich, has interesting overlaps with algebrogeometric questions about rational surfaces, which are not yet completely understood. So there's a lot of interest here, but it's complicated and it's not well understood. So Stefan Bauer actually was able to compute explicitly these multiplicities that occur in the moduli spaces, and it followed from that computation that, in fact, if two Dolgochevs were deformation equivalent, then the elementary symmetric function, well, the p squared plus q squared minus p squared plus q squared, in fact, were the same. So he got a more precise finiteness result. Later, Bob computed the SO3 invariance instead of the SU2 invariance, and together with Bauer's result, he completely finished off that the map from deformation classes of Dolgochevs to diffeomorphism types is 1-to-1. I guess I should insert at this point, this was all pre-Seiberg-Witten. You can do this with Seiberg-Witten, and it's quite a bit easier, as many things are. Okay. So using the higher Donaldson polynomial invariants, which I haven't said anything about, but they're analogs for higher V2 plus, where you don't have to deal with chamber structures anymore. On the face of them, they're invariants. Anyway, Simon worked all of that out. And using those invariants, Bob and I went on to show that the map from deformation types to diffeomorphism types is finite to 1 in general. Of course, the real, it should be clear from my introduction, the real content of this is about elliptic surfaces. Minus infinity and 0 have already been dealt with. 2 is general type, so you automatically have finiteness theorems. You don't know anything about those finiteness theorems except that they're finite. The elliptic surfaces, we had to prove finiteness for the elliptic surfaces of higher genus, and we were able to do that. Later, Tom Rufka and I, and then independently Andras Stipsitz and Zoltan Szabo, showed that, in fact, the map from deformation classes to diffeomorphism classes for elliptic surfaces of higher genus in general is a 1-to-1. And again, one can prove that using Seiberg-Witten a lot easier than Tom and I had to work. Okay. So I'll finish with where I started. As I've just been saying, all these results came before the introduction of Seiberg-Witten invariants. And while they can all be established, often with much less work, using the Seiberg-Witten invariants, one of my messages to you today was these anti-self dual moduli spaces have beautiful geometry and topology, much more intricate than that of the Seiberg-Witten equations. And we don't use them much anymore, but I'm hopeful that we shouldn't forget them, for I'm hopeful that they have much more to teach us, more than we can learn from these points that are the Seiberg-Witten solutions. But that remains to be seen. Thank you. Questions? Comments, Bob? Simon.
One of the interesting questions from those days is whether if you take a Dollar-Chev surface and multiply it by a two-sphere, then whether those are symplectically equivalent.
Yeah.
I'm not sure. You haven't wrote this one here yet, but I'm not sure whether that's actually whether.
So you know they're diffeomorphic by general high-dimensional theory,
Diffeomorphic.
but are they symplectically equivalent?
So presumably, there's some relation between the Gromov and Whitman variance when you multiply by.
That was the so there's the work of Jongbeen in that direction. I'm not sure whether he actually covered these. So the Gromov-Whitman is stable under.
Is there anything that that one learns from this? I mean, it's very interesting that the vanishing locus of a generic self-dual harmonic two-form plays a big role in these arguments, and we still don't seem to know so much about what possibilities are. Is there non-trivial information that one gets from this point of view that has been kind of overlooked using other techniques? I mean, I guess there's sort of elementary geometric ways of introducing and annihilating circles. But.
Well, it has been studied. There's a program on Cliff Clouds from some years ago to extend results, or to prove a correspondence between the Seiberg-Witten and holomorphic curves and respectively similar structures, which I think has been carried through by Chris Gehrig recently. It's been a program.
By whom?
A student in Berkeley called Chris Gehrig.
Chris Gehrig.
But it's a bit disappointing that you have this nice geometry of this form, but then John and Tom Rofka came up with a stabilization trick.
Right.
Means you don't need to
And
use
some with CP2 and use the SO3 invariants. Yeah.
so,
Yeah, it certainly doesn't play a role here. I mean, this is a nice way of canceling and basically canceling it out and for these invariants. But yeah, we have, if you go to SO3 invariants, in general, you often, things that were causing you trouble before because of reducibles or the trivial connections, suddenly they're not an issue anymore. So.
So if there are no more